Hello everyone, my name is Arpit Sharma and today I am going to present my paper titled Using Answer Set Programming for Commonsense Reasoning in Winograd Schema Challenge. This work has been accepted as a full paper in the applications track of ICLP 2019. Let us start with the outline of this presentation. In this presentation, I'm going to give a brief introduction to the Winograd Schema Challenge problem, which is what I am tackling in this work. Then I'm going to go over the contributions of this work. Firstly, I will explain the graph-based representation of a Winograd Schema Challenge problem and a knowledge that I have explained or defined in this work. Second, I'm going to explain a graphical reasoning algorithm for the Winograd Schema Challenge that is also defined as part of this work. Third, I'm going to give an answer programming based implementation of the reasoning algorithm. And fourth, and finally, the evaluation of the Winograd Schema Challenge reasoning algorithm and its answer programming implementation will be provided with respect to the Winograd Schema Challenge corpus. Finally, I will conclude this presentation by giving my remarks and findings and talking about a few important points about this work. So let us start with the introduction now. Uh, Winograd Schema Challenge problem was proposed as an alternative to Turing test in 2011. It contains question answering problems such that to answer question one must read a sentence and perform a pronoun resolution with respect to an entity or a pronoun in the sentence. For example, the first sentence here, the man could not lift his son because he was so weak, and the question, who was weak, can be answered with respect to the sentence by resolving this he to man correctly. Now, as part of the problem, the two answer choices are also provided. Now, this problem is difficult because it requires common sense knowledge or additional knowledge to answer these questions. Why? Because uh, the corpus of the Winograd Schema Challenge contains problems corresponding to each problem, such that only one or two words are different in the corresponding problems. For example, here weak is replaced by heavy, and the answer to the question completely changes. That is, in this case, son is the answer, and in the first case, man is the answer. So, as I was mentioning, to answer these problems, one requires knowledge and reasoning with that knowledge. Now, what kind of knowledge do we need here? We can say that the knowledge that someone being heavy prevents her to lift someone else is the knowledge that we need. Or we can write that same knowledge as, if person 1 cannot lift someone because person 2 is weak, then person 1 is same as person 2, right? Now that was the problem introduction. Now let's take a look at the contributions of this work, which explain how we tackle this problem and how we try to solve this problem. So the first contribution is graph-based representation of a Winograd Schema Challenge problem and a knowledge that is needed to solve that problem. Before going into the representation of a Winograd Schema Challenge problem, let us define a graph-based representation of a sequence of sentences in English. I'll explain in the next few slides how this is useful in representing both knowledge and Winograd Schema Challenge problem. A graph-based representation of a sequence of sentences is an edge-labeled and directed acyclic graph, such that it has a set of nodes N, a set of edges E, and an edge labeling function F. Now the set of nodes are made up of two types of nodes, N1 and N2. These are two sets. Now n1 represents the set of token nodes in the input text, where token nodes are defined with respect to the words in the input sentence. For example, blue nodes here in this graph or set of nodes is a, a representation of the nodes that are present in the n1 set. For example, here lifted underscore 2 is a token node, where underscore 2 represents the index of lifted in this sentence or sequence of sentences. Now n2 contains nodes which are a representation of classes or concepts corresponding to the token nodes. For example, here lift represents the concept of lifting, lifted, and person represents the concept of Tom and Paul. Now there are two types of edges in this graphical representation. The first kind are used to connect two token nodes. So E1 here contains edges from the nodes in N1 to the nodes in N1, where N1 represents a set of token nodes. Now E2, the other set of edges, contains edges from the nodes in N1, that is token nodes, to the nodes in N2, that is concept nodes or conceptual class nodes. Now the edge labeling function f takes an edge and labels it with some relation, semantic relation. Now if an edge belongs to E1, this set E1 set, that is an edge between two token nodes, then this relation edge label comes from a predefined set of labels L, semantic relations L. I'll explain later how we get these semantic relations and where do we get these from. But for now, as we are defining just the graphical representation, so I won't go into details of that because this is very general. Now, the label of the remaining edges, that is the edges in the set E2, are labeled as instance of. Now, once we have a representation of a sequence of English sentences, we can use that to define the graphical representation of a Winograd schema challenge problem. For example, if we have this problem, the man could not lift his son because he was so weak. We can represent this sentence or sequence of sentences as we represented the sequence of sentences in the previous three slides. So when this is represented as a sequence of sentences, our task is to represent the pronoun in it. I'll explain later while explaining the reasoning process why do we need representation of the pronoun. Also, we need to represent the answer choices in the input problem. So the pronoun is represented as a node in this graph. Similarly, two answer choices, man and son, are also represented as man underscore 2 and son underscore 7 in this graph based on their occurrence in the input sentence. Now let's move on to the graphical representation of a knowledge. So let's take the same example that we took earlier. Someone being weak prevents her to lift someone else. Or if person 1 cannot lift someone because person 2 is weak, then person 1 is same as person 2. Generally, this can also be written as if S, then X is same as Y, where S is an English sentence, like person 1 cannot lift someone because person 2 is weak, and X and Y are two tokens in S. So similar to the previous representation, there are tokens in this sentence S, and X and Y represent those two of those tokens. Now, if S then X is same as Y is the generalized representation of a knowledge in this case, then S is an English sentence X and Y are tokens in S, and there are two simple steps in which this knowledge, this type of general knowledge, can be represented as a graph. First step includes representing S as a graph similar to the Winograd Schema challenge sentences, right? As a sequence of sentences was represented as graphs. Now in step 2, x is same as y is represented as two edges, x to y and y to x, in the G graph that was created in step 1, and both of those edges are labeled as is same as in here and here. Here is an example of a knowledge and its graphical representation. As you can see, the if S part represents this is represented as this graph, and the then part, person 1 underscore 1, oh I'm sorry, there is a typo here, it has to be person, is same as person 2 underscore 7 is represented by using these two is same as edges. Now that we have represented or defined the graphical representations of a Winograd schema challenge problem and as knowledge, next step or next contribution of this work is to define graphical reasoning framework or algorithm for these representations. Now, the first step in the Winograd schema challenge reasoning algorithm or Whisker algorithm is to extract a subgraph from the Winograd schema challenge sentences graph. So if you remember, we generated a graph for the Winograd schema challenge sentences or the sentences in a Winograd schema challenge problem. Now in this step, we extract a subgraph from that bigger graph. Now the highlighted part here represents that extracted subgraph. If you can pay attention to this graph, you can easily notice that it contains all the token nodes and none of the concept nodes, like weak is not considered, so is not considered, b is not considered, and so on and so forth. Now also the edges between those non-concept nodes or token nodes are also considered as part of this graph or subgraph in step 1. Similarly, in step 2, we extract a subgraph from the knowledge graph. So here is this entire graph, it represents the knowledge that is listed on top of it, and the highlighted part is the extracted graph from step 2. As you can see here, similar to the subgraph from step 1, all the highlighted nodes represent token nodes. But there is one difference here. In this case, we also do not extract the is same as edge that was created because of the then part of that knowledge. So it disregards that also, or those two edges also, between person 2 underscore 7 and person 1 underscore 1. Now in step 3, our task is to detect a graph subgraph isomorphism between subgraphs from step 1 and step 2. Let us call these highlighted graphs as G1 and G2 respectively. Here the graph subgraph isomorphism means we have to extract a set of node pairs xi, yi such that when each yi in G2 is replaced by xi in G1, remember xi in G1, then this G2 becomes a subgraph of G1. Okay. Now there's a catch here. Now as part of isomorphism, we have to extract node pairs. Now those node pairs have to also match concepts. For example, week 12, week underscore 12 from this G1 graph can only be mapped with week underscore 9 here. Okay, keeping the condition that when it is replaced by this node, when week underscore 9 is replaced by week underscore 12 and so on and so forth, all this highlighted subgraph of G2 or node replaced graph of G2 becomes a subgraph of G1. That is true, but also it has to match. So for each node pair that we have in the isomorphism, we also want them, both the nodes, to be of the same concept. Okay, now here at the lower part of the screen you can see the isomorphism example extracted from these two graphs, where week underscore 12 comma week underscore 9 is one pair, lift underscore 5 lift underscore 4 is another pair, and whenever we replace week underscore 9 in G2 by week underscore 12 and so on so forth, all of these replacements are made, then G2 or the node replaced G2 becomes a subgraph of G1. Now, in the fourth step, once we have the isomorphism set, and we also know that the pronoun is he underscore 9, we know from the representation of the Winograd schema challenge problem, and we also know that answer choices are man underscore 2 and son underscore 7. Then in this step, we take the knowledge graph and all of this information and perform a sequence of operations. First operation is to identify from isomorphism pairs what node in the knowledge graph corresponds to the pronoun to resolve. In this case, it's person 2 underscore 7. Now the next step is to figure out which node person 2 underscore 7 is same as. Here in this case it's person 1 underscore 1. The next step is to map person 1 underscore 1 in the isomorphism set and figure out which node it corresponds to in the input Winograd schema challenge sentence sys graph. Now it corresponds to man underscore 2. Now we see if man underscore 2 is one of the answer choices, and it is one of the answer choices, so the final answer is man underscore 2. Now this was the graphical reasoning algorithm for Winograd schema challenge that was explained or defined as part of this work. Now we move on to answer programming based implementation of this reasoning algorithm. First of all, we need to represent the graphs that we defined or graphical representations that we just defined into answer programming paradigms. To do that, we use three or rather five predicates. First one is has underscore s of arity 3, which is used to represent an edge in the representation of Winograd schema challenge sentences. For example, if you can see this graph here represents a Winograd schema challenge problem or sentences in a Winograd schema challenge problem, and this graph is represented as this set of has underscore s triples. Similarly, we represent knowledge graph by using the predicate has underscore k, and the pronoun in the Winograd schema challenge problem is represented as pronoun of by using pronoun predicate of arity 1. Similarly, answer choice 1 and answer choice 2 are represented by using predicates ans underscore ch1 and ans underscore ch2. Now to implement the first step of the Whisker algorithm or Winograd schema challenge reasoning algorithm, these three rules in ASP were written. So the first rule extracts node x from the input sentence or input representation of Winograd schema challenge sentences. And the second rule also extracts a node. Both of these nodes are token nodes, because as you can see here, we are not considering the edges that are labeled as instance of edges. In step 3 or third rule S13, we extract edges between those tokens. In the predicate edge underscore g underscore s. Similarly, step 2 was implemented in answer set programming by using these three lines of code. The only difference between these three lines and the other three lines that we went through in the previous slide is that in this case we also do not consider the is same as edge. Now the third step is the most important step in this algorithm, which is to extract graph subgraph isomorphism between subgraphs from step 1 and step 2. Now we start uh, with the using matches x comma y as a node pair. So if you remember, in graph subgraph isomorphism we have to detect pairs of nodes from g1 and g2, such that when all the nodes in one graph are replaced by other nodes, then it becomes a subgraph of the other graph. Now we extract those pairs as part of matches predicate of arity 2. Now in step or rule 31, we make sure that all possible pairs of matches or all possible pairs are generated in the isomorphism set. Now the next rules, next 3, 4, 5, 6 rules are used to remove the unnecessary answers from the answers generated in by the rule S31. For example, in rule number S36, we make sure that both x and y in matches, any of the matches pairs, are of same concept, or they belong to the same concept. If they don't, then we remove that answer set. Now here, if we want to add more functionalities, for example, if you want to make sure that the two nodes which are part of a pair, matches pair, are also synonyms, then we can add that rule also. I'll explain how that can be added by using just simple 3 rules in the conclusion section. And that makes this reasoning algorithm implementation in answer set programming very, very important. By changing just few lines of code, we can add a whole new functionality to it. Now, as part of step 4, we have these 5 rules. The first 4 rules are used to extract answer from each of the graph subgraph isomorphism that is generated in the previous step. Now the last rule, S45, is used to make sure that the system or the algorithm does not answer all answers or both the answers as answers. So if that is the case, then we remove that answer set, even if there are no answer sets left. Now that was the simple implementation of the Whisker algorithm in answer set programming paradigm. Now, as part of evaluation, we performed 3 experiments with respect to this work. In the first experiment, we automatically translated Winograd schema challenge problems into graphical formats by using an in-house parser called kparser, which is also available on GitHub. The needed knowledge was manually written in graphical format for the 240 eligible Winograd schema challenge problems. All the 240 problems were correctly answered with respect to the knowledge. In the second experiment, the needed knowledge was not manually written, but it was provided as if s then x is same as y format. Both Winograd Schema challenge problems and the needed knowledge were automatically converted into graphs by using K-parser. 200 out of 240 problems were correctly answered. The 40 problems were not answered because of parsing errors. In experiment 3, we automatically attempted to extract the needed knowledge from Google search in graphical format. The details of this approach, how this knowledge was extracted, are present in our paper, and I would like you to please go through that. And if you have any issues, you can always email me. The Winograd Schema challenge problems were automatically translated into graphs by using K-parser. 120 out of 240 problems were correctly answered using this approach. The remaining were not answered because of unavailability of knowledge and some because of incorrect parsing of input. Now, in conclusion, we present an attempt to solve the Winograd Schema challenge by using additional common sense knowledge. We defined graphical representations for Winograd Schema challenge problem and needed knowledge. We also defined a graphical reasoning algorithm and its ASP implementation. The ASP implementation is easy to generalize by using new constraints. For example, adding below rules, which I was mentioning in the section as well, allows synonym information in information isomorphism extraction step. For example, we can just say two nodes are valid nodes if they belong to same concept, and they are also valid if they are synonyms. And we can say that two nodes do not match or they are not part of isomorphism if they are not valid. That way we can add synonym information as well. That's all I have for this presentation, and if you'd like to know more details about the work, please feel free to contact me on this email, and uh, please read the paper and let me know your comments. Any questions? Thank you.